Okay, welcome to my channel. This time we are going to talk about the finite element method. This method mostly used in mechanical engineering, civil engineering, or also in architecture. And other field of engineering can be used also this method. The basic principle of the method is from elements and note stress and strain. We see here the stress actually equals to force divided by A. And the Hooke's law shows that F is K by X. X is displacement, K is the constant of the spring, and F the force is the force. So we can see that sigma also equal to E by strain. E is the strain and module of elasticity. And A is the cross section area. F is the force. And this is the stress. This is the very basic principle to move to the next calculation, next method of finite element. So from here, we see that F divided by A equal to, and F is AE. Note that the strain is delta L divided by L. Delta is the displacement, L is the initial length. So we have F is AE divided by L delta L. This is the basic formula to calculate the force equals to the area, modulus elasticity, initial length, and delta L. We start from one element to show you the example to apply this formula. Let's say this is the simple element here. We have a rectangular bar here, okay, and here we have force of F. And for instance, L and the area of cross section, let's say 0.0001 meter square, which is, let's say that is the rectangular bar, 0.01 meter, 0.01 meter cross section area. L, for instance, 0.1 meter, and the module of elasticity, let's say 2 × 10⁹ Pascal, and F 10⁵ Newton. Let's say the delta L from this formula. From formula we can see that delta L is actually equals to F L divided by A E. So delta L is F 10 area here, and the E 9 Pascal. Okay, so from here we see delta L is 10⁴, 10⁵, 1/2 It's the method to calculate this by very basic principle of mechanical engineering or physics, something like that. But if we try how to calculate this problem using finite element, very easy. So we convert this formula to matrix multiplication, matrix. Because in finite element we will see more about matrix operation. So how do we write this in matrix operation in finite element? We see that we have here vector of f equal to k 1 minus 1 minus 1 1 vector of, this is the displacement. Finite element is delta L here. Yeah. So how about our formula? Our formula is showing this, so we can rewrite this in very simple. In finite element, we have two nodes, node 1 and node 2. Yeah, it's node 1 and node 2. One element, two nodes. Okay. So from this formula we can see that we can find the value of displacement with the formula. Actually we can see that F here on this node 2, this is fixed. This is fixed. Means that it doesn't move anywhere. Node 1 fixed position, node 2 can move that way because of force F. How to use this formula? So you see that because only two nodes, node 1, F1, F2 equals to K 1 minus 1 minus 1 1, and we have mu1 and mu2. Yeah. Now what is K? K itself is, the K itself is K here. K is, see, yeah, A E divided by L. So K is, the value is, A is 10 power of A area minus 4 A 10 power of 9 by 2 divided by the 10 power of minus 1. So K is 2 10 power of 6 is K. So put here K and you got the matrix. So F1, F2 is the vector of force. Then we have 10 power of 6, 2 minus 2, minus 2 and 2. Okay, and multiply by the vector mu1 and mu2. Alright. This is the K here. Put inside here. Yeah, 2 by 1, 2 by minus 1 is equal to 10 outside. But in this system, node 1 is fixed position. So in boundary condition in mechanical engineering, we can see that this is 0, this is also row and column. And mu1 also, node 1, no displacement, 0 also. So we see that the remaining number here, that F2 equals to 2 10 power of 6 mu2. So mu2 is here. See that mu2 is F2 to 10 power of 6 mu2. What is F2? F2 is 10 power of 5 2 10 power of 6. So we have here mu2 is 0.05 meter. The same result with here. Right? This is the way to calculate the very simple problem of finite element, one element and two nodes. Yeah. Actually, from here, if we deal with more than two elements, or two elements also can be, we see that the factor of mu1 and mu2, actually the inverse of k1, of k, matrix k, by the F1 and F2. Yeah. The inverse of this, we can see the displacement of mu1 and mu2, but the matrix must be inverse. Matrix inverse multiplied by the force. Then you can find the displacement. Very simple. Okay? We can see this problem using the software. So after this, I will try to calculate, to put the data in the software, and we'll see the result of this, whether the same or not, using the software in computer. That's it. Thank you very much. Catch you later. Bye.
Okay, welcome to my channel. This time I'm going to explain how to calculate the finite element problem by using this software, which is so-called LISA. Before we have done with manual calculation and we got the result. Now you want to compare the both results, either the same or not. First of all, you make your own file by click this file, and you may make new or open other file, doesn't matter. And then like this, I put my name there, Dr. Ismail Nawi. And then to begin with, you click this new node and put 0 here. So you see the red node here is node number 1, and node number 2 is 1 meter, 0.1 meter distance from the first one. So we have seen here that make it better the view. These two nodes, node 1 and node 2, already there. Now we are going to make the element by connecting, click this new element, and you click first node and second node. Now we have this element 1 and node 1 and node 2. Now we assign the material, click this default, assign new material, geometry, rectangular bar, the dimension is 0.01, and also this also 0.01, right? And the mechanical properties is isotropic, and Young modulus is 2e9 to 10 power of 9 Pascal, and Poisson ratio 2.5. Poisson ratio 2.5. You can put there for any material, maybe a bit different. So finish this geometry of mechanical, Young modulus or module of elasticity, and Poisson ratio, and geometry is 0.1, 0.1, and the length is 0.1 meters. Okay, now we choose this node, click this, choose the node, and we put the constraint and click this, right click, new displacement, and this 0.1 not move to the x direction, so put it 0 there. Okay, see that? Then the same thing we can see also of y direction, and also the same thing with the z direction. All right, and one more, we try to put the no rotation on z direction. Okay, so node number 1 is fixed already, doesn't move. Now, where's the force? The force is on node 2. So we put the force there, right click and new force, put 100,000 Newton. Okay, see the light green here is the force acting on node 2. Now everything is okay now. So we check again, we check the material, check the material, we have the geometry and mechanical, all right. Geometry 0.01, 0.01, okay, finish. And then we check the displacement XYZ and force. Check the force again. The force is 100,000 Newton on X direction, yeah, at node 2. Now we solve by click this equal sign and you got the result straight away. You see it 0.05. The same result we got when we calculate by manual method. So this red color here is moved 0.05 meters, the displacement. If you want to see the animation, we can click this and we play the animation. See this? We have seen that this area doesn't move really. It's fixed here, node 1, but node 2 move 0.05 meter to the right way. And also we can see that the other color, the yellow one is about 0.03 and the green one 0.02 and the blue one is 0.001 and the very dark blue here is doesn't move at all. It means 0 meter displacement. This is very simple for the one element and two nodes, and the result is the same with the manual calculation we have done before. Thank you very much. My name is Dr. Ismail Nawi. I will see you later on. Thank you.